Hi students, hope you are doing great. Welcome to Electron Chemistry Center, abbreviated as ECC. Now, in today's lecture, we are going to discuss about a topic called hybridization in chemical bonding and molecular structure. So, before going into hybridization topic, let me tell you what is the need of hybridization. Why we supposed to discuss hybridization? So I can explain with the help of an example. Let us take formation of methane molecule. In methane molecule, carbon is the central atom. Atomic number is 6. Electronic configuration is 1s2, 2s2, 2p2. 2s has 2 electrons, 2p has 2 electrons. This is the ground state electronic configuration. In ground state, carbon has 2 unpaired electrons. That indicates it can form only 2 bonds. When it comes to excited state, 1 electron from 2s orbital can be promoted to 2p. Then it becomes 1 in 2s. And it becomes 3 in 2p. So total 4 unpaired electrons are there in first excited state. It indicates it can form 4 bonds with 4 hydrogens. Then you will get 4 CH bonds. 4 CH bonds. By seeing orbital diagram, these 3 bonds are identical and this bond is different. Experimentally, it was proved that all CH bonds are identical. Why it is happening like that? It can be understood with the help of a concept called hybridization. Hybridization explains you why all CH bonds are identical in methane molecule. Now let me tell you the definition of hybridization. Hybridization is nothing but intermixing of atomic orbitals. Intermixing of atomic orbitals of almost similar energy. Of almost similar energy to give new set of hybrid orbitals. To give new set of hybrid orbitals of identical shape and same energy. Identical shape and same energy is called hybridization. It is intermixing. When atomic orbitals, if they undergo intermixing of almost similar energy, they will give new set of hybrid orbitals, and these hybrid orbitals must be of identical shape as well as same energy. This phenomenon is called hybridization. Now we need to discuss about conditions of hybridization, or you can say salient features of hybridization. What are the conditions of hybridization or salient features of hybridization? So let's see the conditions of hybridization. What are the conditions of hybridization can be given? Now we come to know about the definition of hybridization. Now we are discussing about conditions of hybridization or salient features of hybridization. First thing, in hybridization we are intermixing atomic orbitals. Atomic orbitals of same atom. Atomic orbitals of same atom can be involved in hybridization. Atomic orbitals of same atom can be involved in hybridization. Let us say I am taking 2s orbital and 2p orbital. This 2s orbital and 2p orbital are involving in hybridization, and both these 2s and 2p atomic orbitals must belongs to same atom. then only hybridization is possible. That is the first condition. Now second condition, atomic orbitals of similar energy can be involved in hybridization. So what does it mean? Similar energy in the sense, let us say I have taken 2s orbital and 2p orbital. If I try to intermix, they will undergo intermixing. They will undergo hybridization. If I take 2s and if I try to intermix with the 5p atomic orbital, this is not possible. Why? Because 2s atomic orbital energy is different from 5p atomic orbital energy. So this intermixing is not possible. But the first one is possible. Why? Because they possess almost of similar energy. Right? Now if we see few more conditions here. And condition number 3, number of hybrid orbitals formed. Number of hybrid orbitals formed is equal to number of hybrid orbitals formed is equal to number of atomic orbitals involved. Number of atomic orbitals involved. Like how many atomic orbitals are involved? Those many hybrid orbitals can be found. Let us say if 2 atomic orbitals are involved, then 2 hybrid orbitals will be formed. If 3 are involved, 3 can be formed. And this hybrid orbital, and these are the major conditions. You can see the features of hybridization also. Right? In that, hybrid orbital consists of, if you see the hybrid orbital, this is the structure of hybrid orbital. It consists of a larger lobe. This lobe is large lobe, and this lobe is smaller lobe. These are the 2 lobes possessed by hybrid orbital. Among these 2 lobes, large and smaller lobe, large lobe is effective in bonding, whereas smaller lobe is not much effective in bonding because it is close to the nucleus. Whenever it is close to the nucleus, it cannot be involved in bonding easily as compared to large lobe. So this is a very important condition. So in most of the cases, large lobe will be involved in effective bond formation by overlapping. And this is a major feature of a hybrid orbital. And let's continue with the types of hybridization. Let me discuss types of hybridization. So in that, first I will consider atomic orbitals S and P. By involving S and P, there are 3 types of hybridization. First is sp hybridization. So one s orbital and one p orbital is involving. As I already told you, number of hybrid orbitals formed is equal to number of atomic orbitals involved. Here 2 atomic orbitals are involving. It indicates you will get 2 hybrid orbitals. These 2 are 2 sp hybrid orbitals. And if I take sp2 hybridization, one s orbital, and how many p orbitals are there? 2 p orbitals are there. It is 1 p orbital and it is another p orbital. So 1 plus 2. So total how many hybrid orbitals will get it? 3. We will get 3 hybrid orbitals. Similarly, I can consider sp3 hybridization. sp3 hybridization, 1 s orbital and similarly 3 p orbitals. If 3 p orbitals are involved, then total you will get 4 hybrid orbitals, and these 4 hybrid orbitals I am giving. So as you know that each hybrid orbital consists of a large lobe and small lobe also. And if you consider d orbitals involvement, if d orbitals are involved, there are other 3 types of hybridization. sp3 d. Here one s orbital is involving, as well as 3 p orbitals are involving, as well as 1 d orbital is involving. Total number of atomic orbitals are 5. In such cases, you will get 5 hybrid orbitals. You will get 5 hybrid orbitals. Now, next one, sp3d2. In sp3d2, if you observe it, it is 1 s atomic orbital. And how many p orbitals are there? 3. And there are 2 d orbitals. And total, you will get 3 plus 2, 5, 5 plus 1, 6. Total 6 hybrid orbitals will be formed. You get total 6 hybrid orbitals are formed. Now, if you consider one more, that is the last type of hybridization, I'll take it. sp3d3. I'll take sp3d3. In this, one s orbital is there, plus 3 p orbitals are there, plus 3 d orbitals are there. Total you will get 7 hybrid orbitals. Total you will get 7 hybrid orbitals. One more, which is 7 hybrid orbitals. Right? If you consider all these are the different types of hybridization. One is sp hybridization, and second one sp2 hybridization, sp3 hybridization, sp3d hybridization, sp3d2 hybridization, and last one sp3d3 hybridization. Students, let's start with first type of hybridization, that is sp hybridization. In sp hybridization, what will happen? Intermixing of one s orbital with one p orbital will give 2 sp hybrid orbitals, in which percentage of s character is 50%. Similarly, percentage of p character is 50%. 50% s character and 50% p character. I can make you to understand sp hybridization with the help of an example, beryllium chloride, in which beryllium is central atom. Beryllium atomic number is 4, electronic configuration is 1s2, 2s2, and 2p0. In 2s orbital, there are 2 electrons, and 2p orbital is empty or vacant orbital, you can say. It is the ground state electronic configuration of beryllium. In ground state, beryllium cannot form any bond, as there are no unpaired electrons. One electron from 2s orbital can be promoted to 2p. That will take place in excited state. So in excited state, electronic configuration becomes 2s1, and one electron will be there in 2p. It will be 2s and 2p. This 2s atomic orbital will undergo intermixing with 2p atomic orbital. By intermixing, it will form 2 sp hybrid orbitals. Let us take 2s orbital, and it is 2p orbital. And these two can undergo intermixing. If these two can undergo intermixing, you will get 2 sp hybrid orbitals. And these two sp hybrid orbitals of beryllium, as I already told you the condition, atomic orbitals must belongs to same atom. 2s also belongs to beryllium and 2p also belongs to beryllium. And these two hybrid orbitals can be arranged in a space in such a way where electron pair repulsions are less. In that way they can arrange. If these two sp hybrid orbitals are arranged in a linear manner, electron pair repulsions will be less, and this arrangement gives more stability to the molecule. This is one larger lobe and smaller lobe, and it is one larger lobe and a smaller lobe. It is one sp hybrid orbital of beryllium, and it is another sp hybrid orbital of beryllium. Now, Chlorine atom, if you consider, chlorine atomic number is 17 and electronic configuration is neon 3s2 3p5. 3s has 2 electrons and 3p has 5 electrons, in which this 3p orbital has one unpaired electron. This unpaired electron present in 3pz orbital, the 3pz orbital of chlorine atom can undergo overlap with sp hybrid orbital of beryllium. It will undergo overlap. This is the 3p orbital, or you can write 3pz orbital of chlorine. Similarly, this way 3p orbital of chlorine. Another chlorine atom also you need to take it. 2 chlorine atoms, which gives a linear shaped molecule in which beryllium is central atom, and this overlap gives you a sigma bond. This sigma bond is formed by overlapping of sp hybrid orbital of beryllium and p orbital of chlorine. Similarly, here also sigma bond is formed, and this sigma bond is formed due to the overlap of sp hybrid orbital of beryllium and the p orbital of chlorine. As you know that end-on end overlap always leads to the formation of sigma bond, and beryllium forms a sigma bond with the chlorine, and similarly here also one more sigma bond with the chlorine, and with a bond angle 180 degrees. It gives a linear shaped arrangement. So sp hybridization is possible in BeCl2 molecule, which gives a linear shaped arrangement with a bond angle 180 degree. If you arrange this molecule with 180 degrees, it gives less electron pair repulsions and more stability to the molecule. This is the best example you can consider for sp hybridization.
Start, sir.
Hope you understand sp hybridization. Let's move to the second one, sp2 hybridization. sp2 hybridization, in which what will happen? One s atomic orbital and 2 p atomic orbitals will undergo intermixing. There is a lot of difference between intermixing and overlapping. Intermixing is the term which will be involved in hybridization concept. Overlapping is the term that comes in VBT concept, valence bond theory. That I will do it in next lecture. sp2 hybridization, percentage of s character, if you consider, percentage of s character is 33.33%, whereas percentage of p character 66.6%, in which I will consider one example, formation of boron trifluoride molecule. How BF3 molecule is formed, in which boron is central atom whose atomic number is 5 and electronic configuration is 1s2 2s2 2p1. 2s has 2 electrons while 2p has 1 electron. What does it indicate? In ground state, boron can form only one bond because one unpaired electron is present. In excited state of boron, one electron is promoted to 2p and 2s becomes 1 and 2p becomes 2. Now there are 3 unpaired electrons, one is in 2s and 2 are in 2. This 2s orbital of boron can undergo intermixing with 2 2p orbitals of boron, same atom only, will give you, it is one 2s orbital and it is one another 2p orbital and it is one more 2p orbital. This will give you 3 hybrid orbitals. This will give you 3 hybrid orbitals. And these 3 hybrid orbitals should be arranged in space in such a way that where electron pair repulsion should be minimized. It gives the stability to the molecule. Now let's see how these 3 hybrid orbitals can be arranged. This is the way how 3 sp2 hybrid orbitals are arranged. It is one sp2 hybrid orbital, it is second one, and it is third one. Larger lobe, smaller lobe, large, small, and large, small. And sp2 hybrid orbital, and it is sp2 hybrid orbital, and it is sp2 hybrid orbital. Now there are 3 sp2 hybrid orbitals, and all these 3 sp2 hybrid orbitals are of identical shape. So shape is identical. In such cases, all bonds must be identical. Now if you take fluorine, atomic number is 9 and electronic configuration is 1s2, 2s2, 2p5, in which 2s is having 2 electrons and 2p is having 5 electrons. 2p is having 5 electrons, in which 2pz orbital consists of 1 unpaired electrons. That indicates like that if you consider 3 fluorine atoms, each fluorine atom has 1 unpaired electron. 3 fluorine atoms has 3 unpaired electrons, and this 2pz orbital of fluorine can undergo overlapping with sp2 hybrid orbital of boron. Similarly, another fluorine atom can undergo overlap, and with this sp2 hybrid orbital also 2pz orbital of fluorine can undergo overlap. Here if you observe, it is the 2pz orbital of fluorine. Now it is the 2pz orbital of fluorine. Similarly, it is 2pz orbital of fluorine. sp2 hybrid orbital will undergo overlap with 2pz orbital of fluorine. It leads to the formation of sigma bond. This sigma bond is formed by overlapping of sp2 and 2p orbital. Similarly, sigma sp2 2p. This sigma also formed due to overlap of sp2 2p orbital. Remember that hybridized orbitals always leads to the formation of sigma bonds. Whenever unhybridized orbitals are there, those unhybridized orbitals will lead to the formation of pi bonds that we will discuss in organic compounds. Now it is the central atom boron, in which fluorine is linked like this, and another fluorine and another fluorine, which gives an arrangement called trigonal planar. With the bond angle 120 degrees. That means sp2 hybridized molecule will be having a bond angle of 120 degrees and the shape is trigonal planar. For that example we have discussed BF3. Hope you understand sp2 hybridization. Let's move on to third type of hybridization, sp3 hybridization. In sp3 hybridization, percentage of S character 25% and percentage of P character is 75%. Percentage of S character and percentage of P character will give you important facts, and that will be discussed in the forthcoming sessions, in which for sp3 hybridization I'll take a best example, that is methane, formula CH4, in which carbon atomic number is 6 and electronic configuration is 1s2, 2s2, 2p2, where 2s has 2 electrons and 2p has 2 electrons. This is ground state configuration for carbon. In ground state, if you see, there are 2 unpaired electrons. What does it mean? Carbon can form only 2 bonds in ground state. But as you know, actually carbon can form 4 bonds. In excited state, 1 electron from 2s is promoted to 2p. Then 2s2 becomes 2s1, 2p becomes 2p3. Total we got 4 unpaired electrons. in which one 2s atomic orbital can undergo intermixing with 3 2p atomic orbitals. I'll give you in the form of a diagram. It is one 2s atomic orbital and 3 2p atomic orbitals are there. Right? And total how many are there? 4 atomic orbitals are there. You will get 4 hybrid orbitals. These are the 4 hybrid orbitals. And these 4 hybrid orbitals can be arranged in such a way in space to reduce the repulsions. Let's see how these hybrid orbitals can be arranged in space. Now these are the 4 sp3 hybrid orbitals. sp3 hybrid orbital, it is also sp3 and sp3 and sp3. These 4 sp3 hybrid orbitals are arranged in such a way of 4 corners of tetrahedron. So it gives an arrangement called tetrahedral arrangement. Now as you know that hydrogen atomic number is 1, electronic configuration is 1s1. It has only one unpaired electron in 1s atomic orbital. This 1s atomic orbital can undergo overlap with sp3 hybrid orbital of carbon. It gives a sigma. This sigma is formed due to sp3 1s overlap. This is hydrogen. Similarly, here also overlapping is possible, here also overlapping is possible, and here also overlapping is possible. These are the 4 hydrogens. It gives sigma bond. This sigma bond is sp3 1s, and this sigma bond is also formed due to sp3 1s, and this sigma bond is also formed due to sp3 1s. Like that, carbon can form 4 sigma bonds. Why? Because all these are the hybridized orbitals only, in which carbon is the central atom. Now it is connected to hydrogen, and it is connected to another hydrogen, and it is connected to another hydrogen, and one more. It gives a tetrahedral arrangement. This is a tetrahedral arrangement if you observe, and in which the bond angle is given as 109 degree 28 minutes, and the shape of the molecule is tetrahedral molecule. And it is an example of sp3 hybridized molecule. And if you observe that here we have explained percentage of s character, percentage of p character, how electronic configuration will be in ground state as well as in excited state, how many hybrid orbitals are formed, how these hybrid orbitals are arranged, and what is the shape of the molecule we have given with the help of sp3 hybridization.
Start.
Hope you understand the first 3 types of hybridization: sp, sp2 as well as sp3. Now let's make a look on it. If d orbitals are involving hybridization, that is sp3d hybridization. Somehow it's interesting factor. Let's see. In which one s orbital is involving plus 3 p orbitals are involving plus 1 d orbital is involving. Hence total hybrid orbitals are 5. It gives 5 sp3d hybrid orbitals. For that, I'll take a best example for sp3d hybridization, PCl5, phosphorus pentachloride, in which phosphorus is the central atom. Phosphorus atomic number 15 and electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3. This is the electronic configuration of phosphorus, and it is having 3d, but it is vacant to 3d orbital. And if you consider 3s is having 2 electrons, 3p is having 3 electrons, and 3D is empty. 3D is empty. This is the configuration in ground state. In ground state of phosphorus, it consists of 3 unpaired electrons. What does it mean? It can form only 3 bonds. In excited state, 1 electron promoted to 3D. In excited state, 1 electron promoted to 3D. So it will become 1 3s, 3p, remains same, 3 unpaired electrons. 1 electron is promoted to 3D. Total, if you observe it, total 5 unpaired electrons are there. 1 is in 3s, 3 are in 3p, and 1 is in 3d. So these 5 unpaired electrons which are present in respective atomic orbitals will undergo intermixing. So you will get 5 sp3d hybrid orbitals, and these 5 sp3d hybrid orbitals will be arranged in such a way. See here, phosphorus, it is having 5 sp3 hybrid orbital, and here 1 sp3d hybrid orbital, and another one, and third one. These 5 sp3d orbitals will be arranged in trigonal planar shape, and another sp3d hybrid orbital will be above the axis and one will be below the axis. These 3 sp3d hybrid orbitals will give trigonal planar shape, and these two will give a pyramidal shape. If you observe here, there are pyramidal in the sense one is above the axis and another one is below the axis. Now here 5 chlorine atoms are there, in which 3 chlorine atoms can be arranged in a trigonal planar, and remaining 2 chlorine atoms, one is above the axis and another one is below the axis. It gives a shape called trigonal. This is trigonal, and it is bipyramidal. Trigonal bipyramidal arrangement it will form. Why? Because with this 4th bond it can form pyramid, as well as with this 5th bond also it can form pyramid with trigonal planar shape. Hence it is called trigonal bipyramidal. And these bonds which are forming trigonal planar shape, these bonds are called equatorial bonds. And these bonds which are forming bipyramidal shape are called axial bonds. Like that, PCl5 consists of 2 types of bonds. One is equatorial bonds and second one is axial bonds. And this trigonal planar shaped one having a bond angle of 120 degree, and these axial bonds are perpendicular to the equatorial bonds. Hence the bond angle is given as 90 degrees. It is 90 degree and this bond angle is 120 degree. That is, it is possible because of the presence of vacant 3d orbitals in phosphorus. Hence PCl5 can undergo sp3d hybridization. It gives a trigonal bipyramidal shape.
Start.
Hope you understand sp3d hybridization, children. Now let's start next type of hybridization, sp3d2 hybridization. It's very simple concept compared to other concepts in chemical bonding. Why? Because all these types of hybridization follows same genre of understanding. Like here also what you will say, 1 s orbital will be involved and 3 p orbitals will be involved and 2 d orbitals will be involved. Total 1 plus 3, 5, 5 plus 2, 6. You will get 6 sp3d2 hybrid orbitals. And now let's take a look how these sp3d2 hybrid orbitals will be arranged in a particular molecule. For that I am taking an example, sulfur hexafluoride, whose formula is SF6, in which central atom is sulfur. Z is equal to 16 atomic number, And electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4 and 3d 0. Vacant 3d orbitals are there. So 3s has 2 electrons. Now 3p has 4 electrons. Now 3d is vacant. 5. So 3d is vacant, it is 3s, 3p, 3d. It is ground state configuration. In ground state, there are 2 unpaired electrons for sulfur in 3p orbitals. What does it mean? It can form only 2 bonds. Now let's go to first excited state. In first excited state, what will happen? 3p electron promoted to 3d. 3s remains same. It will be having 2 electrons. And in 3p, you will get 3 unpaired electrons as 1 electron is promoted to 3d. Remaining all these are vacant. Now if we consider second excited state. In second excited state, what will happen, students? This 3s electron also promoted to 3d. Then 3s becomes 1, 3p becomes 3. Now 3d becomes 2. Total we got 6 unpaired electrons in second excited state. So sulfur can form maximum 6 bonds. It can form 2 bonds in ground state. It can form total 4 bonds in first excited state. It can form 6 bonds in second excited state. Now in second excited state, 3s orbitals and 3 3p orbitals and 2 3d orbitals will undergo intermixing. It will give 6 sp3d2 hybrid orbitals. And these 6 sp3d hybrid orbitals will be arranged in such a way to avoid repulsions. 4 fluorine atoms will form a square planar shape and 2 fluorine atoms will be forming in this way. So if you observe the shape properly, it gives a square planar arrangement. One is above the square planar and another one is below the square planar. Now, if you join all this, so sulfur is the central atom. Now this sulfur is connected to 4 fluorine atoms. One fluorine atom is in this way and another fluorine atom is in this way. If you observe, we can't say it as square bipyramidal. This shape is not square bipyramidal. Why? Because most of the people under impression that it forms a square. One is above the axis and another one is below the axis. Why can't we call it as a square pyramidal? It is not square pyramidal. Why? Because sulfur is in the central atom and it is connected to 4 fluorine atoms. And one fluorine atom is above the plane, and with this fluorine atom, 4 corners are forming. With this fluorine atom, another 4 corners. Remaining fluorine atoms. These 4 fluorine atoms can form another 4 corners, which gives total 8 corners. 8 corners makes the SF6 molecule in the form of an octahedron, which gives an arrangement called octahedral arrangement. Hence, shape of SF6 molecule is octahedral molecule. If any molecule possessing sp3d2 hybridization, it is having octahedral shape. But we are not talking about lone pair of electrons here. If lone pair of electrons are present, shape might changes. Due to the presence of lone pair of electrons, shape might changes. That will be discussed in BSCPR theory. We are not discussing about the lone pair of electrons and how they affect shape in hybridization part. And in which, if you observe it, all these bonds are perpendicular to each other. Hence, bond angles are 90 degree. Bond angles are 90 degree. Here these are 90 degree and these are also 90 degree, you can see. Now it is about S of 6 whose hybridization is sp3d2 and the shape is octahedral and the bond angle is 90 degree. Now let's make a look on it. Third type of hybridization in which d orbitals are involved, that is third type, but the whole it is the sixth type of hybridization. On the whole, if you consider it is sixth type of hybridization, but only for d orbitals it is third type of hybridization, sp3d, sp3d2, sp3d3. So you can say easily sp3d2 hybridization means 1 s orbital and 3 p orbitals, 3 d orbitals. Total 7 sp3d3 hybrid orbitals are forming. 7 sp3d3 hybrid orbitals are forming. 1 s orbital, 3 p orbitals and 3 d orbitals will undergo intermixing, which gives 7 sp3d3 hybrid orbitals. And let's see how these can be arranged. I'll take an example, iodine heptafluoride, IF7, where iodine is central atom and its outermost electronic configuration is 5s2, 5p5 and 5d0. It is vacant. 5s has 2 electrons, 5p has 5 electrons and 5d has 0 electrons. It is vacant orbital. This configuration is in ground state. Now as you know that in first excited state, what will happen? One electron from P can be promoted to D. So 5s remains same, then 5p, 2 electrons will be here, 1 electron will be here and 1 electron, and in 5d 1 electron will be there. Now in second excited state, this electron promoted to D, then 5s becomes 2, 5p becomes 3 and 5d becomes 2. 2 unpaired electrons will be there. Now one more excited state is also possible for iodine, that is third excited state. In third excited state what will happen? Even 5s electron also can be promoted to D. In that case, what it will give? It is 1 unpaired electron and it is 3 unpaired electrons are there. And in 5d, you can see 3 unpaired electrons are there. Total we got 7 unpaired electrons, in which 1 is in 5s, 3 are in 5p, 3 are in 5d. That indicates these 3 types of atomic orbitals will undergo intermixing. Total number of atomic orbitals which are undergoing intermixing are 7. If 7 atomic orbitals are undergoing intermixing, it will give 7 sp3d3 hybrid orbitals. And these 7 sp3d3 hybrid orbitals, how they will arrange? Iodine is connected to 3 fluorine atoms in this way. Now another 2 fluorine atoms. It is forming a pentagon and one fluorine is above the axis and another fluorine is below the axis. One fluorine is above the plane and another fluorine is below the plane. It gives a shape called pentagonal bipyramidal. It gives a shape called pentagonal bipyramidal. These 5 fluorine atoms are forming pentagonal and 2 fluorine atoms are forming bipyramidal shape. One is above the plane and another one is below the plane. And these bipyramidal fluorine atoms making a bond angle of 90 degrees with pentagonal fluorine atoms, and these pentagonal fluorine atoms making a bond angle of 72 degrees. Like that, two types of bond angles are possible in IF7. One is 72 degrees and another one is 90 degree. So any sp3d3 hybridized molecule will be having pentagonal bipyramidal shape in the absence of lone pair of electrons. If lone pair of electrons are there, the shape might changes. That will be explained in BS-EPR theory. Yes children, so far we have learnt about different types of hybridization. In this lecture, we had started hybridization topic and we had completed. Definition of hybridization we had discussed first, followed by conditions of hybridization and features of hybridization we have discussed, and types of hybridization also we have discussed. There are total 6 types of hybridization. One is sp, sp2, sp3, sp3d, sp3d2, sp3d3. These are the 6 types of hybridization we have discussed. For sp hybridization, BeCl2 is an example, and the shape of molecule is linear. sp2 hybridization, boron trifluoride, BF3 is an example. Shape of molecule is trigonal planar. And sp3 hybridization, example is CH4, and the shape of molecule is tetrahedral. sp3 dehybridization, PCl5, and the shape of molecule is trigonal bipyramidal. sp3d2 hybridization, we have discussed an example SF6, and the shape of molecule is octahedral. And the last one is sp3d3 hybridization, example IF7, iodine heptafluoride, and the shape of molecule is pentagonal bipyramidal. Pentagonal bipyramidal. And for linear, bond angle is 180 degree. Trigonal planar bond angle is 120 degree. Tetrahedral bond angle is 109 degree 28 minutes. Trigonal bipyramidal possessing 2 bond angles. One is 90 degree and another one is 120 degree. Octahedral possessing 90 degree. Pentagonal bipyramidal also possessing 2 bond angles. One is 72 degree and 90 degree. This is the whole summary of today's lecture. In next lecture, we are going to discuss a shortcut of hybridization. What is the shortcut can be used to find out hybridization in any molecule? As you know that all competitive examinations are time-based examinations. In such cases, if you want to find out hybridization of any molecule within a less time, I'll give you a shortcut in my next lecture, and as well as few more examples we will solve it, and previous yearly asked questions based on hybridization also we will be solving in the next lecture. Please watch us and subscribe to this channel for more updates. Thank you. Have a nice day.